Hello everyone. So today I'm going to talk about something that's absolutely fundamental to mass spectroscopy, that is ionization techniques. We'll be covering the major methods like APCI, EI, ESI, and several others. So let's dive right in. So first things first, what exactly is ionization and why do we even need it? Well, ionization is basically the process where we convert neutral molecules into charged ions. And here's the thing, mass spectrometers can only detect charged particles. Without ionization, we literally can't analyze anything. Now, there isn't one size fits all approach here. The ionization method you choose really depends on what you're working with. So you need to consider things like how big is your molecule? Is it polar or non-polar? Can it handle heat or will it fall apart? Is it volatile in nature? So all these factors, they play a role in deciding which technique to use. Think of it like choosing the right tool for a job. You wouldn't use a hammer to tighten a screw, right? So same principle applies here. Alright, so let's talk about how we classify these techniques. Broadly speaking, we have two main categories, hard ionization and soft ionization. Now in hard ionization techniques, these are like taking a sledgehammer to your molecule. They transfer a lot of energy which causes extensive fragmentation. Now that might sound bad, but it's actually really useful because those fragments give us structural information. Now the examples of hard ionization is electron ionization. On the other hand, soft ionization techniques are much gentler. They use low energy, so you get minimal fragmentation of your molecular ions. This is great when you want to know the molecular weight or when you're working with delicate molecules. And the examples of soft ionization techniques are ESI, APCI, MALDI. These, these all are soft ionization methods. So depending on what information you need, you'll pick one over the other. Let's start with one of the oldest and most established techniques, that is electron ionization. So here how it works. Your sample molecules gets bombarded with high energy electrons. We are talking 70 electron volts here. These electrons essentially knock out electrons from your molecules, forming what we call radical cations. Now, electron ionization is a hard ionization technique. So, as I mentioned earlier, you get extensive fragmentation. But here's the cool part. This fragmentation is highly reproducible. That means the same molecule will always break apart in the same way under the same conditions. So what makes EI really valuable is that we have this massive spectral libraries. So you can compare your fragmentation pattern to your known compound and identify what you have. It's like having a fingerprint database for molecules. But EI does have limitation. It only works with volatile compounds, things that can vaporize without decomposing. So we are talking about smaller molecules generally under 1000 Daltons. Also, sometimes the molecular ion peak is so weak or even absent because of all that fragmentation that is happening. Still, EI is the go-to technique for GCMS analysis and is widely used in environmental and forensic analysis. Now let's move to something completely different, that is electrospray ionization. This one really revolutionized mass spectrometry, especially for biological molecules. The principle is pretty elegant. You spray your solution through a charged needle, which creates this fine mist of charged droplets, and as the solvent evaporates, the charges get more and more concentrated on the droplet surface. Eventually, the ions are released into the gas phase. This is a soft ionization process, so your molecule stays intact. One of the coolest things about ASI is that it produces multiply charged ions. So instead of just M plus H, you might get M plus 2H with a charge of 2 plus, M plus 3H with 3 plus, and so on. This is actually amazing because it extends the mass range of your instrument. So a protein with a molecular weight of 50,000 could appear at 5,000 master charge if it has 10 charges. That means you can analyze really large molecules on instrument with limited mass ranges. ESI is perfect for polar ionic compounds, especially for large molecules like proteins and peptides. It works at atmospheric pressure and is easily coupled with liquid chromatography. And talking about the downsides is that it requires your sample to be polar and ionizable. It doesn't work well with non-polar compounds. Also, you have to watch out for matrix effects and ion suppression. Things like salt in your sample can really mess up your signal. Despite these limitations, electrospray ionization is absolutely dominant in proteomics, pharmaceutical analysis, and pretty much any application involving biological macromolecules. Next up is atmospheric pressure chemical ionization. This is sort of middle ground between ESI and older techniques. Here's how the APCI works. Your sample solution gets nebulized and heated. So we are talking about 200 to 500 degrees Celsius. This vaporizes everything. Then you have a corona discharge that ionizes the solvent molecules. And these ionized solvent molecules then ionize your analyte through ion molecule reaction. It's chemical ionization but happening at atmospheric pressure. APCI is still a soft technique, so you get mostly intact molecular ions like M plus H or M minus H. But it's not quite as gentle as ESI. There's some heat involved. The big advantage of APCI over ESI is that it handles less polar compounds better. It also it is also less affected by salts and matrix effect, and it can tolerate higher flow rate. So if ESI isn't giving you good result because of your compound isn't polar enough, so APCI might be your answer. The trade-off is that you need thermally stable compounds. If your molecule falls apart at high temperature, APCI won't work. Also, it's not great for really large molecules like proteins. APCI is commonly used for steroids, lipid, drug metabolism studies, and small to medium sized molecules, generally under 1500 Daltons. It's very popular in pharmaceutical analysis and environmental work. Now coming to chemical ionization, It is somewhat similar conceptually to APCI, but done in a vacuum rather than at atmospheric pressure. In chemical ionization, you first ionize a reagent gas. Could be methane, ammonia, or isobutane. Then these reagent ions react with your sample molecules through proton transfer or other ion molecule reaction. So you end up with protonated molecules, that is M plus H in positive mode, or deprotonated molecules, that is M minus H in negative mode. Now this chemical ionization, it is softer than electron ionization. So you get much more prominent molecular ion peaks and less fragmentation. This makes it really useful for determining molecular weights, especially when electron ionization gives you too much fragmentation to see the molecular ion. Chemical ionization is complementary to electron ionization. You can use both on the same sample to get different information. Electron ionization gives you structural details through fragmentation, and chemical ionization confirms your molecular weight. Like electron ionization, chemical ionization requires volatile samples. So it's mainly used with GCMS. It's particularly useful when you need reliable molecular weight information for thermally stable volatile compounds. Now let's talk about MALDI, that is matrix assisted laser desorption ionization. This technique is particularly important for analyzing large molecules. The process is interesting. You mix your sample with a UV absorbing matrix compound and let them co-crystallize on a metal plate. Then you hit this with a pulsed laser. The matrix absorbs all that laser energy and transfers it to your analyte, causing soft desorption and ionization. Unlike ESI, MALDI typically produces singly charged ions. So you get M plus H, not multiply charged species. This makes the spectra much simpler to interpret, especially for complex mixtures. MALDI can handle enormous molecules. We are talking about 300,000 Daltons. It's the technique of choice for intact protein analysis, polymer characterization, and oligonucleotides. It's also become huge in imaging mass spectrometry, where you can map the distribution of molecules across a tissue section. The main challenge with MALDI is choosing and preparing the right metrics. The metrics can interfere with analysis, especially for small molecules. Also, it's not great for quantitation compared to ESI. But for qualitative analysis of large biomolecules, MALDI is unbeatable. It's also become the standard for bacterial identification using system like MALDI-TOF. So let me briefly mention fast atom bombardment or FAB. This is an older technique that mostly has been replaced by ESI and MALDI, but it's worth knowing about. In FAB, you dissolve your sample in liquid matrix like glycerol, then bombard it with high energy atoms, usually xenon or argon. Then the energy transfer causes desorption and ionization. It was useful for polar, non-volatile compounds back in the day, but the liquid matrix causes interferences and the technique has limitations. You'll rarely see it used in modern labs, but it was an important stepping stone to current techniques. Field ionization and field desorption are specialized techniques that use very high electric field. In field ionization, the electric field is so strong, it literally pulls electron out of the molecules. It's extremely soft, producing almost exclusively molecular ions with very little fragmentation. In-field desorption is similar but designed for non-volatile samples. You apply a sample to a special emitter, apply high voltage and get simultaneous desorption and ionization. These techniques are useful for non-polar compounds and can provide complementary information to electron ionization. However, they are quite specialized and not commonly found in every lab. So the last technique I want to cover is atmospheric pressure photoionization. In APPI, your vaporized sample is exposed to UV photons. These photons ionize either the analyte directly or a dopant compound, which then transfers the charge to your analyte. Now APPI fills a niche that ESI doesn't cover well, that is non-polar compounds. It also has a minimal matrix effect and less ion separation compared to ESI, which is a real advantage. The technique is used for things like non-polar drugs, steroids, lipids, and environmental contaminant. It's not as popular as ESI or APCI, but when you have non-polar analytes, APPI can be the best choice. Okay, so let's put all this together in a comparison table so you can see the difference at a glance. Electron ionization is hard ionization, best for volatile non-polar compounds under 1000 Daltons with extensive fragmentation. Coming to chemical ionization, it is soft ionization technique, also for volatile compounds under 1000 Daltons but with minimal fragmentation. ESI is again soft, perfect for polar and ionic molecules of any size with minimal fragmentation. APCI is soft, works well with moderately polar compounds under 1500 Daltons and minimal fragmentation. MALDI is soft, excellent for large biomolecules over 1000 Daltons, and here also you'll find very minimal fragmentation. APPI, the last one, is also soft ionization designed for non-polar compounds under 1500 Daltons, also with minimal fragmentation. So you can see each technique has its sweet spot. So how do you actually choose which technique to use? Let me give you a practical framework. First, consider molecular weight. If you're working with large molecules like proteins, polymers, you're looking at ESI or MALDI. And for smaller molecules, it is electron ionization or chemical ionization. Second, you need to think about the polarity. Polar compounds, ESI is the best bet. If it is non-polar, then consider APCI, APPI or EI. Third, volatility. If your compound can be vaporized, electron ionization or chemical ionization are options. Non-volatile, then you have to move back to ESI or MALDI. Fourth thing is thermal stability. Can your compound handle heat without decomposing? Then APCI or EI are fine. If it is thermally labile, then you have to stick with ESI or MALDI. Fifth, what information do you need? If you need structural details through fragmentation, go with EI. If you just need the molecular weight, soft techniques like ESI are better. And finally, what form is your sample in? If it's in solution, ESI is convenient. If it's volatile, electron ionization work well. There's no perfect technique for everything. It's all about matching the techniques to your specific needs. So let me quickly summarize where each technique shines in real world application. ESI dominates in proteomics, drug discovery, and anything involving biological molecules. Electron ionization is the workhorse of environmental analysis, forensics, and analysis of volatile organic compounds. APCI is heavily used in pharmaceutical analysis, metabolomics, and lipid analysis. MALDI is the go-to for protein identification, polymer characterization, and tissue imaging. Chemical ionization is used for molecular weight confirmation and as a complement to EI and GCMS. And APPI finds its niche in analyzing non-polar drugs and environmental pollutants. So depending on your field, you'll probably use some techniques much more than others. Alright, let's wrap this up with some key takeaways. First and most important, there is no single technique that's best for everything. Each has its strengths and weaknesses. Second, selecting the right technique depends entirely on your analyte properties, that is size, polarity, stability, and volatility. Third, modern mass spectrometry labs often have multiple ionization options available, and experienced analysts know when to switch techniques. Fourth, ESI and MALDI have really taken over for biological application, while EI remains the standard for GCMS work. And finally, understanding ionization isn't just academic. It's absolutely crucial for developing good methods and getting reliable results. The better you understand these techniques, the better analyst you'll be. You'll know when a method isn't working because you're using the wrong ionization technique, and you'll know how to fix it. That's it. I hope you liked this video, and if you have any questions, you can put it down in the comment section. Thank you.